Okay, so closing this session here, I'm going to be talking about the farther future as we enter the era of electron endeavors here at RHIC by way of adding an electron beam in the far future, about the early 2020s, to the existing facility. So how does the program enabled by adding an electron beam fit into the science of RHIC? And if we're going to think about this question, I think it's important first to step back and consider why we built RHIC in the first place. And I think the broadest answer to that is that we built RHIC to study QCD. So as Steve Victor has said, it's of course an accelerator-based program, but it's not designed to be at the energy or the intensity frontier as many accelerator facilities are. It's actually more closely analogous to many areas of condensed matter research. The goal is to create a system and then study its properties. So what systems are we studying here at RHIC? We're studying simple QCD bound states, in as much as anything in QCD can be considered simple. The proton is the simplest stable bound state in QCD. Conveniently, nature has already created it for us. We're studying collections of QCD bound states, i.e. nuclei, also available out of the box. And we've known for a number of years that nuclei are not just straightforward superpositions of neutrons and protons. So there's a more rich structure going on there. That's what makes it so interesting to look at. And then we're studying QCD in a regime where it's so hot and dense that we have deconfinement. The quarks and gluons are deconfined, no longer in colorless bound states. Of course, the quark-gluon plasma for this sum-assembly in the laboratory is required. So an underpinning strategy through the history of RHIC has been to understand more complex QCD systems within the context of simpler ones. RHIC was designed from the start as a single facility capable of nucleus-nucleus, deuteron and proton nucleus, and proton-proton collisions for exactly this purpose. So I'd like to talk for a few minutes about calibration using different probes. So we already use electroweak probes of the hot, dense matter created in the final state of nucleus-nucleus collisions. So direct photons, internal conversions of thermal photons. At LHC energies, they take advantage of Z bosons, all for the same reason that these are free of the complications of strong interactions. Then we learn in turn by comparing to a variety of strongly interacting probes. We use light mesons as proxies for light quarks, which have various potential means of in-medium energy loss. We look at Charman bottom mesons as proxies for heavy quarks, which are less affected by radiative energy loss due to their mass. Then deuteron-gold collisions have allowed us instead to use strong probes of the initial state, and in turn, electron-ion collisions will enable electroweak probes of the initial state for the first time at collider energies. So I really see it as fitting in very naturally to the strategy that we've been using at RHIC for the past decade. So we've had our fundamental field theory of QCD in hand since the 1970s, but the degrees of freedom in that field theory are quarks and gluons, not the hadrons that we can work with and measure in the laboratory. So as Anne discussed, a lot of the ePHENIX emphasis is on jets, more hermetic detectors. Why is this? I think it's because we really want to access the partons. We want to know more about what's going on at the partonic level. Jets and dijets are among the best handles available to access parton kinematics if you're working with hadronic collisions. If you're working with electron-proton, electron-ion collisions, you can access your parton kinematics instead by measuring simply the energy and the angle of the scattered electron. So I think in general, to continue advancing in QCD, it's going to be critical to perform experimental work where quarks and gluons are relevant degrees of freedom in the processes being studied. So what does this mean? It means we need to have high enough energies such that partonic language is the correct language to describe what we're looking at. And we need to have detectors capable of measuring observables that are sensitive to parton kinematics in whatever collision system we're studying. So we spent a lot of time here at RHIC trying to understand our various cold and hot QCD systems in terms of what the partons inside them are doing. But what about the other side of the confinement coin? The question of how do individual partons turn into hadrons. So hadronization. I think for hadronization, we really have a lot to learn, and we're going to learn it from a variety of collision systems. So what are the ways in which partons can turn into hadrons? Some of the questions we can ask, are there spin momentum correlations in hadronization? We know the answer to that is yes. Some spin momentum correlations have now been measured definitively in E plus E minus annihilation at B factories, with first results published by Bell, 2006, already 5 years ago now, and preliminary results which provided a nice confirmation of the Bell published results that just were released in August from Babar. How about gluons versus quarks? Do they hadronize differently? Is something different going on? Gluon versus quark jets is actually a hot topic at the LHC PP program right now. think what you'd actually want to do would be to go back to clean E plus E minus, look at 2-jet, 3-jet events, with new jet analysis techniques in hand that weren't around when we were working actively with LEP. How is hadronization affected if it's happening in a vacuum, in cold nuclear matter, in hot dense QCD matter? One thing that's nice with electron-ion collisions, you can use the path lengths through nuclei and different energies of your final state produced hadron to benchmark your hadronization times. I think that's pretty neat. Some of the terms we use for hadronization, fragmentation. So fragmentation functions, which describe the probability of a certain flavor quark or a gluon fragmenting, turning into a particular final state hadron, have been very useful over the past decades, but really they're a parameterization, just an empirical parameterization. So what does this really mean? I think we don't really have any sense of what's actually happening there physically, even though we have some very useful tools. Then in heavy ion collisions, we talked about some other concepts. We use the terms freeze out, recombination, though I have to confess I never really had a clear idea of what recombination meant in terms of gluons, what the gluons might be doing. In general, if I had to just give an intuitive sense, I would say that soft hadron production from thermalized quark-gluon plasma involves different mechanisms for hadronization than from a hard scattered quark or gluon. I don't think I could really tell you how, but I think we have a lot to learn there, and that some of it is going to be specific to looking at the hot dense matter created in ion collisions. So also particular to heavy ion collisions, we produce light atomic nuclei and antinuclei here at RHIC. So these are compound QCD systems. They're starting as partons somehow. What's going on here? And does it have any cosmological implications, if we can understand that? So I know this is a lot of words here, but the message to take away is that I really think hadronization has been a largely neglected area of QCD over the past decades. I'd look at this as a positive thing. I think we have lots of opportunities for progress to look forward to in the upcoming years, and I think electron-ion, proton-proton, and heavy ion collisions are all going to play a role along with the traditional E plus E minus annihilation. So the future of RHIC in broad strokes, I think we're going to have more precise measurements. With RHIC's unprecedented flexibility extended further, we'll have even more comparisons and complementarities to learn from, as Anne said at the end of her talk. So we'll have polarized electrons on polarized protons as we already have now, polarized protons on polarized light ions, such as helium-3, polarized electrons on those polarized light ions, electrons on heavy ions, protons and deuterons on heavy ions, light ion collisions, asymmetric ion collisions, heavy ion collisions. This looks like a laundry list, but it's not a list of things to do. It's a list of tools in our toolbox. Our job is to build a science vision, to build a set of physics goals, and to think about which combinations of these tools are going to best help us achieve those physics goals. So in terms of precision, these will all have higher luminosities than are currently available at RHIC now, or were available at earlier facilities. We'll have electroweak and colored probes available in both the initial and the final states for our comparisons and contrasts. We'll have better control over parton kinematics just by measuring the scattered electron's energy and angle in the case of deep inelastic scattering, by measuring fully reconstructed jets, by getting more dye jets via our hermetic detectors, and we'll be able to do these controlled experiments in hadronization. So now, of course, precision experimental measurements in QCD are nice, but will we be ready to really learn and extract physics from them? And I think it's an important question. Is it the right time to build this kind of a facility? My answer to that is yes. I think we're currently in the early phase of a second era of QCD, which I think of as the era of quantitative QCD. I looked at the first 30 years or so as a period of discovery and development, and you can argue about when to end this phase, but I think certainly a symbolic closure is marked by the awarding of the 2004 Nobel Prize to Gross, Pulitzer, and Wilczek for the discovery of asymptotic freedom. I think we're now in the early stages of a more quantitative period. In particular, since the second half of the 1990s, we've been starting to consider detailed internal dynamics that parts with traditional parton model ways of looking at hadrons, and critically, to perform phenomenological calculations using these new ideas and tools. So, some examples. Resummation was developed in the second half of the 90s. I've shown this to the collaboration before, but I like it as an illustration. So this is a paper from George Sturman and Werner Vogelsang, as well as a student of George's, from 2009, and it's for Na24 data, root S of 23.7 GeV. Just 10 years ago, we wouldn't have dreamed of trying to perform perturbative calculations at such a low center of mass energy. And you can see the red curves. They look pretty good, actually. non-collinearity of partons with the parent hadron. Yuji talked about this a little bit. So this is also something that was really worked out in the second half of the 90s. If I don't just neglect the transverse motion of my quark or gluon inside the parent hadron or inside the process, inside the fragmenting jet, I get a whole bunch of spin momentum correlations that can come out. And we now know from data from the past 9 or 10 years that a lot of those spin momentum correlations are in fact non-zero. So again, another development from the 1990s. Various effective field theories have been developed, for one example being soft collinear effective theory over the last 10 years. Here's a paper from submitted in August. It's actually predictions for the Higgs cross-section versus transverse momentum. And in particular, if you look at the low PT area, this is the trickier part to get, if you will. What I like about soft collinear effective theory, even though I'm certainly no expert, is that it's really taking into account both of these things. So they are making use of resummation techniques developed in the 1990s, and it's actually an alternative way of dealing with this non-collinearity of partons, the transverse motion of those partons in the protons colliding at the LHC. And that's what the intrinsic transverse motion of those partons is what is giving this turnover here at very low PT. So now we have tools of soft collinear effective theory to deal with that as well. Now, nonlinear evolution at small momentum fractions, ideas about saturation. The ideas are about 10 years old, and we had a theoretical framework to perform nonlinear evolution about 10 years ago. But if you look at this, it's a PRD, so peer-reviewed article from 2009. Nonlinear QCD-made data is the title. A global analysis of lepton-proton scattering with running coupling BK evolution. And don't worry about what running coupling BK evolution is. The point is that even though we had the theoretical framework in place about 10 years ago, it was only in 2006 that we worked out this running coupling BK evolution. And that's what enabled us to do phenomenological calculations to actually compare to experimental data and therefore learn something from them, or learn more from them. My list goes on. There's been a renaissance in nuclear PDFs in the last few years. I was looking at the EPS09 paper, and it was published in 2009. Actually, I checked, and it was submitted in 2009, so it's been 2 years. It's got 115 citations already. There's a lot of interest in this right now. I've been talking about perturbative techniques so far, but there's also progress in non-perturbative methods as well. Lattice QCD is just starting to perform calculations at the physical point, the physical pion mass. Here's an example from Hatsuda's talk at PHENIX 2011 a few months ago. 2 different collaborations that have performed calculations at the physical pion mass. The publications came out in 2010, 2011, very recent work. And as Bill discussed, ADS-CFT, this gauge string duality, I think it's a very exciting recent development, not because it's quantitative right now, it's completely exploratory right now, but I think it's really exciting because it's the first fundamentally new handle we have to try to tackle QCD in decades. You look at perturbative QCD, this is decades old. Lattice QCD is decades old as well. They're both making excellent progress, and that's great, but I think this is really exciting just because it's new. And I think we can be proud at RHIC that the heavy ion program here has really driven this to more intense advancement, or more intense activity in the past few years. So my answer to the question of is this the right time is yes. I believe it is the right time for such a flexible multi-purpose QCD facility, and bring the data on. So, bring the data on. How do we get started with an electron beam here? Well, the time scale, to remind you, we're talking about is the early 2020s, so 10 years from now. The initial beam energy would be 5 to 6 GeV, to be upgraded over time to 20 to 30 GeV. You would focus first on inclusive and some semi-inclusive measurements, which require less luminosity as well as less detector coverage. Inclusive measurements mean that you're measuring only the energy and angle of your scattered electron. Remember, this gives you full information about the partonic kinematics. Semi-inclusive measurements, you're looking at both the scattered electron as well as at least one hadron in the final state, so any hadronization studies would obviously be semi-inclusive measurements. And then exclusive measurements, which I'm not talking about, you want to measure all your final state particles. So you need very hermetic detector coverage, and you need higher luminosities. Could we use the ePHENIX forward spectrometer to measure our scattered electron? Here's just a basic kinematic plot, Q squared, the 4 momentum transfer squared, versus momentum fraction x. If you look at, this is for 5 on 50, 5 GeV electrons on 50 GeV protons, or 50 GeV per nucleon ions. It's very similar for 50 on 100. And if you make a cutoff at about 1 GeV squared and q squared for our perturbative theoretical friends to be able to work with the data, you would get minimum x coverage down to about 10 to the minus 3, going up to a few times 10 to the minus 2. As Anne said, if we wanted to use this detector for this, we would have to plan accordingly, keep in mind, make a coherent plan from the start. We would need low mass tracking if we want to look at low energy electrons. Remember, it's a 5 GeV electron beam in the beginning. Look at the energy and angular resolutions of our detectors. But what would we be able to do in the very early stages? For example, just looking at now the nuclear parton distribution functions for valence C and gluons. This is from the EPS 09 paper that I showed before, as a function of x. So the coverage would go down to about 10 to the minus 3. So for the gluon, the uncertainties are so large that we would actually be able to make a big impact on this, greatly reduce this uncertainty, just with these very first collisions with a 5 GeV beam. Another example in the spin structure of the proton, here you have uncertainties. This is now the gluon delta G of x, gluon polarization as a function of x, versus momentum fraction x, uncertainties on, from current data and the range, kinematic range of current data. And then you have projected uncertainty. This is based on about 1 month of running with a 5 GeV beam on 250 GeV polarized proton beam. And the data would go down to about here, so a few times 10 to the minus 4. And this would make actually quite a big difference in the chi-squared profile, already from just 1 month of running with a 5 GeV beam and the polarized proton beam that we already have now. This is only for inclusive measurements, so you're just measuring the scattered electrons' energy and angle. So some concepts when we were thinking about the ePHENIX forward spectrometer to begin with. Many of the striking effects related to parton dynamics have been observed at forward rapidities. So this is what motivates a large acceptance forward spectrometer. What kind of parton dynamic effects related to parton dynamics am I talking about? Well, these spin momentum correlations. There are a variety of them, as well as gluon saturation, as nonlinear effects at low parton momentum fractions. So you want full jet reconstruction capabilities to access the parton kinematics, as I've been saying. It also allows you to separate different effects, for example, the Sivers versus the Collins spin momentum correlations in the proton and in the fragmentation process. You want particle ID for pi kp, investigate surprises from some earlier RHIC data, also to study hadronization. Tracking in EMCal was motivated in the case of ePHENIX, looking primarily at PP and, say, deuteron gold measurements by Drell-Yan, being able to do quark-anti-quark annihilation to E plus E minus pairs. So now what's the latest conceptual design for comparison for an EP-EA optimized detector? Well, it's a large acceptance. This is the Electron Ion Collider task force here at Brookhaven. They're looking at a large detector acceptance plus or minus about 5 in rapidity. Low radiation length would be critical to look at low electron energies. They would want precise vertex reconstruction to separate B and C, as we're interested in the Hadron program here at RHIC as well, but with narrower coverage, a Dirk or a Rich for pi kp ID, and they would have forward detectors not shown in this picture to tag protons in exclusive reactions, which I'm not focusing on here. So if you look actually at the hadron going direction spectrometer, so you've got tracking pi kp particle ID, your EMCal, your hadronic calorimetry. It's actually quite similar to what we're talking about for the forward spectrometer in ePHENIX, which was conceived, at least at the cartoon level, for PP and PA collisions. So the designs are similar. It's not a coincidence, because many of the physics goals are similar. So this is something that we can take advantage of. The devil's in the details, which I will not be talking about. Abhay will be talking tomorrow about some more practical considerations. So just a few final remarks here. The heavy ion physics and nucleon structure communities came together at RHIC in the 1990s, not because they identified common physics interests, but because the capabilities of RHIC as an accelerator facility offered valuable opportunities to both of them. The QCD subfields studied at RHIC and elsewhere in the world are at different points in terms of our present level of understanding. But after a long haul, since first running then the QCD Lagrangian in the 1970s, everything is moving in the same direction to finally become more quantitative. As the various subfields in QCD mature, the power they have to strengthen and inform one another is ever increasing. And personally, I think this is what makes it so special to be working here at RHIC. I've certainly learned a lot more physics than I would have if I were working at a single-purpose facility. And working here for the past 10 years now as part of PHENIX has really pushed me to think about the interconnections between the different fields. So, as we talk now, 20 years into PHENIX, about how to extend further the capabilities of our celebrated facility in the years to come, we're in a position to build an even stronger, more comprehensive, and more integrated QCD program than ever. So happy 20th birthday, PHENIX.